Here's my title. It's upside down because the problem I've been working on requires, at least my approach to it, I will hope to convince you, requires thinking in a completely different way. You would normally have to go and solve the Hubbard model, but this is not soluble in 2 dimensions. There is another solvable model, and it's in momentum space. And the work that I've been trying to do is to go from this solvable model to the Hubbard model. And that's what I want to show you how to do. Now, this work is motivated by a bigger question. We are well familiar with Fermi liquid theory, and there's a fixed point, but we don't have a fixed point for Mottness. We don't have something that tells us what are the relevant parameters near a Mott transition, or what kinds of Hamiltonians will give rise to this physics. This has to be a quartic interacting theory, and that's why the problem is hard. So what I'd like to do is just start by reviewing Fermi liquid theory to see what insight we can gain into how one might construct a fixed point for Mottness. So the standard the standard approach in RG is to scale towards the Fermi surface by this component of the momentum, which is now perpendicular. And what you find if you just go through this scaling procedure is that all the local interactions have a positive scaling dimension, which means they're irrelevant. The chemical potential is a relevant parameter, which means the filling is going to be relevant. And if you just go through this, go to one loop order, what you find is that the only instability does not come from local repulsions. It comes from an attractive channel or a CDW channel. And this is the standard statement that the BCS theory really is a fundamental statement because it's the only instability of a Fermi surface. Okay, the question I want to ask is, the chemical potential has scaling dimension -1. Is it possible to find an operator whose scaling dimension is less than -1, and hence it's more relevant? And if you could find such an operator, that would in fact tell you that a new fixed point exists. Okay, so I want to go to experimental data since physics is an experimental subject. Is there any insight we can gain from this? Phil Anderson has been hammered on this a lot. He said that, look, if you look at all of the data, it's telling you fundamentally there's a particle-hole asymmetry. Sorry, I have to go back. Yeah, there's a particle-hole asymmetry. And he was quite annoyed that theorists didn't take this more seriously. Okay, now, why would this have been on Phil's mind? Here's a possible reason. He wrote a paper in 2000 with Duncan Haldane about the symmetries of Fermi liquids. And what they did is they tried to understand in terms of group theory, what are the overall symmetries that Fermi liquids have? Now, this ... scaling to 0 are all of the local repulsions, which of course play no role at the Fermi liquid fixed point. Tau 3 is just the Z component of the Pauli matrices. So you can write Fermi liquid theory like this. Psi is a 2-component spinor. So there are 4 objects which are present in the fixed point of a Fermi liquid. And all of these can be rotated into one another. There'll be proper rotations and improper rotations. They can be classified based on whether or not the determinant for this transformation is even or odd, or if its determinant is 1, or if its determinant is -1. If it's determined as 1, these are proper rotations. and this is the SO4 symmetry. And that's just reflecting the fact that the spin and charge sectors are equivalent for a Fermi liquid. There's nothing that breaks them. If you have an improper rotation, those two symmetries are broken. And the group for the improper rotations is just the quotient of O4 with SO4, and that's Z2. So their point is that there's an extra Z2 symmetry at a Fermi surface. Okay, now what exactly does this symmetry look like? Because it doesn't seem like it's a symmetry of this Hamiltonian. Okay, this paper is not well known. In fact, I've not come across anyone who has read this paper. So let me show you what this Z2 symmetry does. If I just write the four components which get rotated into one another, what I want to do is write them in such a way that I can easily act with the matrix that will make it absolutely clear what the Z2 symmetry is doing. So what I just want to do is take linear combinations. So I have a symmetric and an anti-symmetric combination of the upspins and the downspins. So these are the real operators or the Majorana basis. Now it's clear. If I operate on a matrix in O4, which is an improper rotation, so it has a determinant of -1. If the -1 is down here, it will act only on this component. And what it will do is it will interchange these two. So it's a particle-hole transformation, but for only one of the spin species, not both of them. Okay? Now, this -1 doesn't have to be down here. It doesn't have to be in the antisymmetric component. It could be up here. And then you'll say, oh, well, this doesn't seem like it's doing the same thing. Well, it is, because the way you construct this from these two representations is you take the difference here. If this goes to its negative, then CP is going to minus CP up dagger. Okay, so either it's going to its Hermitian conjugate or the negative of the Hermitian conjugate. Okay, now when is this a symmetry? If you're right at the chemical potential, your Hamiltonian is equal to 0, which means that I can, with impunity, make this transformation in O4 with impunity. This just goes to itself, and this goes to 1 minus this. So their whole point now is that what really defines a Fermi liquid is that it's a state of matter in which you can make this transformation at the chemical potential. So their point now is that to break Fermi liquids, all you have to do is destroy this Z2 symmetry. Okay, so this is your basic Hamiltonian for a Fermi liquid. And their point now is that if you added something here, you want to maximally break this. The simplest term that maximally breaks this is this term right here. And it's not only that it breaks the symmetry, is that it has to have a scaling dimension less than -1. Okay, this is odd under Z2, and it has scaling dimension -2, because there's only one momentum integration here. So this is a relevant interaction. This is, you have to define, there has to be a new fixed point. And this, in fact, is the Hatsugai Kohmoto model. So a way of lifting Hatsugai Kohmoto out of the dark recesses of everyone's minds is that it really is the model that maximally breaks Z2, and it has to define a new fixed point. Although it looks like the model has nothing to do with reality. I will get to that in a minute. Okay, now why should breaking Z2 tell you something new? Well, here's what it has to do with the charge gap. If I just construct this operator, so it's CP up times 1 minus the occupancy, so it only acts on empty sites. I call this operator this, and if I add to this, which will act on singly occupied sites, I have two different ways of writing the electron operator, two things that contribute to this. Under Z2, there should be no energy difference between these, and these should be equivalent. In fact, that's what happens. Under the Z2, this becomes this. So in fact, these two just get interchanged. So they are degenerate. If you break Z2, this interchange symmetry goes away, and you have to open an energy gap. And this state will no longer be equivalent to this one. And that's exactly what the Hatsugai Kohmoto model does. And the Z2 symmetry is central to the opening of the gap. That's why this band just looks like this, and this one just looks like this. And the surface between them is the surface of zeros, which is essential to Mott physics. You know, this is just what this looks like right at half filling if U is much bigger than W. So if U exceeds the kinetic energy, this band lies above the chemical potential, and you just have a surface of zeros. If U is less than W and you're still at half filling, you will have a singly occupied sector which sits below the chemical potential. So you have three kinds of occupancies: empty, lying above, and singly occupied and doubly occupied. And the surface of zeros will just be between the two singly occupied parts. Okay, so this will describe a metal, and yes. Okay, and note, the spectral weight which was up here is transferred down here. And so even at this level, there is spectral weight transfer in this model. It's not dynamical spectral weight transfer, which is the really non-trivial part that really figures prominently in Mottness. These surfaces come about by a self-energy which is divergent. Okay, now one can ask the question, are there any local perturbations of this model which take you away from this Mott point? Okay, and you can easily go through this analysis. You can expand around just, if you had just one surface that, one filling surface that crossed the chemical potential, or two, you can calculate the beta function for any local interaction, including Hubbard, and you would get zero. So there are no local perturbations of this, and it makes sense. This interaction is inherently non-local, and hence there should be nothing local that would destroy it. Okay, so right, so including Hubbard, this is stable to that. So the phase diagram or the flow diagram for this looks the following. Any local interaction will not destroy the Mott physics that I have outlined from HK. The superconductor that arises from this was detailed in the first paper we wrote on this, and it's a very different superconductor than BCS. I'm not going to talk about that, but I just want to outline that the Z2 symmetry is completely the thing that determines the new structure of this fixed point. Okay, so that's fine, but what is it good for? If this fixed point is useful, it should be able to tell us about Hubbard physics. Now, how far away? It looks like we're very far away from Hubbard physics. Hubbard physics is not just a single sum over momentum with opposite spins. It looks like this, where you have mixing between all the possible momenta. Is there any way of going from here to there? Well, there is. One can systematically start including mixing between two K points, which differ by pi. So you just group the K points in your Brillouin zone, into clusters, you can first start with 2. You simply hybridize these. You will lift the degeneracy, which is one of the problems with the Hatsugai-Kohmoto model. And then you can ask the question, how many momentum states do you have to include to get Hubbard physics? Okay, so this procedure is very well, very easy to document. You mix k and k plus pi. And if you just let this momentum be just 0, 0, and pi, you can rewrite the the new mixed momentum Hatsugai-Kohmoto model in identically the same way as you would the Hubbard model. You can then represent this by the sums and differences, the molecular states for this cell, and you can sum over the cells, and you'll end up with exactly the same structure for the Hamiltonian. Okay, and you'll have as many of these terms as you do momenta that you have mixed. So each one of these looks just like an HK model, but it has the momentum mixing in it. So the momentum mixing doesn't take you away from the fixed point if you don't have too many momenta. Okay, so the generalization, you have n momentum scattering. This decreases the size of the Brillouin zone. So this is just things now that differ by pi, and here you'll have pi over 4. Every time you do this, you'll be decreasing the size of the Brillouin zone. There's a dual representation in terms of a real space construction in terms of the cells. And if you now let n go to infinity, there will be no sum over momentum anymore, and you'll just have a sum over this local degree of freedom, or the number of cells you have, and hence this has to go to the Hubbard model. Okay, so
Philip, may I ask a question? Am I correct that as soon as n is larger, strictly larger than 1, in contrast to the original HK model, the kinetic and potential energies no longer commute in this model?
They no longer commute. That's the key point. So we have the key ingredient that makes the complication of the Hubbard model something to worry about.
Thanks.
Okay, but n equals 2, you can still go, because you're just diagonalizing a 2 by 2, you can, or 4 by 4, you can still go and do that. Okay, so if n isn't too big, you can still go and solve it. But now I just want to ask the question, how large does n have to be to reproduce what we know about the Hubbard model? Okay, so this is a test. This is one dimension. E Hubbard infinity is a Hubbard chain, and this energy comes about from solving beta ansatz. This is we should have called it something more creative than the orbital Hatsugai-Kohmoto model. It's usually called the momentum mixing Hatsugai-Kohmoto model. And but nonetheless, that's just what it is. And this is for n is now how many momenta you have here. And what you find is this energy difference relative to the energy in, so I'm looking at the relative deviation here, goes to 0 fairly quickly as you increase the number of orbital mixings that you have, or momentum. So already at n equals 10, you have basically 1% difference. And as you start increasing n further, this will go roughly to 0. And how it goes to 0, I will tell you in about 5 minutes. Okay, so this is working. Now, you can't just ask the question about the ground state. You need to ask the question about how well do we get the excited states? So, in other words, what is the energy gap in this model? Okay, in beta ansatz, the energy gap scales like this. Some number, and this goes to C over U. So there's an essential singularity. This is what we get for the orbital HK model. And this is now as a function of the orbital number, or the number of momentum states we have now as our mixing. And at u equals 0, we're getting that this gap is going to 0. This dashed line is what you get from beta ansatz. And this is approaching this line. Now, there is a benchmark in this. And let's look at, and the benchmark is DMRG. Okay. No, we are not limited by the gap scaling like 1 over the length of the system. It's the charge gap scaling like that. Because since we already have a sum over momentum, we're technically in the thermodynamic limit, and hence there's no programmatic problem with there being with the gap actually being 0. That's not the case in DMRG. Now, DMRG solved with open boundary conditions, and I'll show you a change a little later. And as a result, the gap at u equals 0 does not vanish. And if we just compare the similar sizes of systems we see now, in fact, any size of system, you'll never get that this thing vanishes. Okay? And Stephen White is very honest about it. You say, look, that's clearly the behavior you are going to see. Okay? Now, the thing of it is, you can do better than this. This is open boundary conditions. If, in fact, you use periodic boundary conditions, and since this is inherently formulated as a twist in the boundary conditions, if you sample the momentum, which are the minimum excitations across the gap, you should be able to get the gap correctly. And that's what we did here. So we just did DMRG with periodic boundary conditions, and in fact, we got this thing to go to 0. Okay, so it's not an inherent problem in DMRG getting 0 at u equals 0. You can't solve that problem. And that came about entirely from the insight we gained by solving the orbital HK model. Okay, now let's go to 2D. If you look at just 2 orbitals, we just have mixing between 0, 0, and pi, pi. This is what the density of states looks like as we crank up u. U equals 0. There's a central peak, and this is the density of states for the non-interacting system. And as you crank up u, unlike the single orbital Hatsugai Kohmoto model, there is no critical value of u that you need before you get a dip in the density of states. And it does so without going through a central peak. And this is the answer. If you look at other cluster methods for the 2D problem, there is no critical value of u. And this is just n equals 2. If we go to now, and okay, there's a charge gap, and this is just a summation over momentum with 2 orbitals per site. So this is a very inexpensive calculation. Now, if you can increase the cluster size, and this is n equals 4, it's a 2 by 2, and you get more detail, you start to see additional peaks here, and the width of these bands gets narrower, which is a crucial part of Mott physics. But once again, there is no central peak, and this just vanishes, and you get a gap in the system. Okay, now we can compare with EQMC, cluster perturbation theory, and other methods. This is what the spectral function looks like. And we can compare with the best simulations that we have done. This is just what happens in the 2 by 2, just looking at just the spectral function from before. But our best calculations so far is the biggest ones are in a 4x4. So it's 16 orbitals on a square lattice, just solving the Hatsugai Kohmoto model with all of this momentum mixing. So there's 16 momentum states here, and this is what we get. And this doesn't look so different from the lower band over here. Okay, so that's good. Okay, now let's go and do something else. Okay, let's address this issue of how well does this converge? Okay, let's look at d equals 1, where we know the exact answer. Okay, so here we simply solve this linear chain of orbital Hatsugai Kohmoto using DMRG. We don't have to go and do exact diagonalization. But we did DMRG now with periodic boundary conditions, not open boundary conditions. Okay, and this is how it's converging. So we're looking at the energy difference relative to beta ansatz. And as you see, this is converging faster than 1 over n. The actual convergence, and this is, we went up to n equals 40. Now you might say, well, what happens if you did bigger than that? Look, you can always say that, so I don't view that question as being serious. N equals 40 is certainly big enough to see any sort of pathological trend that's going to happen. This is converging as 1 over n squared. Okay, why is it converging so rapidly? It's converging so rapidly if you just look at how many new interactions do you have as you start introducing this index right here. Well, there are n squared of them. But this is still controlled by the HK fixed point. And hence you're making n squared deviations from this, and hence the convergence should scale as 1 over the number of degrees of freedom. So that all checks. Now, we can generalize this to d dimensions. The number of degrees of freedom per linear dimension is n squared, which means in d dimensions, it's n to the 2d. The convergence to scale is n to the 2d, I mean 1 over n to the 2d, which means if you're in d equals infinity and n is bigger than 1, there are no corrections, which means that n equals 1, assuming there's continuity between n bigger than 1 and less n equal to 1, there are no corrections to this. But d equals infinity is something you know, okay? D equals infinity is DMFT, which means that as far as solving for the ground state energy is concerned, or at least the essence of Mott physics, but the gap, HK and DMFT are in the same universality class. In fact, this gives you a way of thinking about why DMFT works. The fluctuations in terms of momentum mixing completely go away. Okay, now, one thing we can look at are the antiferromagnetic correlations. They do seem to grow as you increase U and as you cool the system down, which is the correct thing. Of course, we're in a finite system, so we finite temperature. We don't expect to see a full antiferromagnetism, but we are seeing an indication of the susceptibility increasing. Okay, is everything gapped? No, it's not. The spin sector is not. If you look at the heat capacity, so it scales as a linear function of temperature, which means they're low energy excitations. And since we have some analytical control, we can actually find the dispersion for these excitations. And the next the lowest lying spin state is s equals 1, which means it's bosonic. There's a gapless s equals 1 excitation, which is giving rise to this linear behavior of the heat capacity. Okay, so that's our statement about the low-lying spin part of this problem. Okay, and so this is telling you if they are spin-ons, they're not the ones which are generating this, they're bound. Okay, let me close by looking at our plot of n of k, since we can get this accurately without doing any analytical continuation. We're just doing an exact diagonalization. What does this look like? So if we just use this data, which hasn't evolved so much, you find that there is a region here where you have some poles, and it doesn't extend all the way to the zone boundary. That is significant because the green function has to change sign here, the real part, which means that if you take a path that goes like this, you have to account for the sign change somehow. The only way to do that is if there is a line of zeros, either going from here to there, or on the backside of this, there have to be zeros. Okay, so we can accurately get n of k, and here's what it looks like in our 16 orbital. This is the 4x4. And as we change the doping, the nature of the zeros changes fundamentally. So this is the non-interacting system in sort of pink or orange, and the black are the poles or the Fermi surface. The dotted region is the surface of zeros. And as you increase the doping, these two surfaces merge and do this. But it's clear, this surface here does not equal this one, which means these surfaces have fundamentally different volumes or areas, which means that the non-interacting volume is not equal to the interacting one, which means that there is the Luttinger count doesn't work, with the Luttinger count strictly being the count that you obtain by looking at all the sign changes of the green function. There's a deviation from that. And I've written lots of papers on that. And it's fairly clear that if you have a self-energy that's diverging, the Luttinger-Ward functional does not exist, and hence there's no basis for the theorem in the first place. Okay, so here's the bottom line. If you include momentum mixing, you can do this systematically. If you're at the Z2 breaking fixed point, n equals infinity, you have to end up with Hubbard. But the take-home message is that you don't need n very big to get Hubbard operationally. It's all converging very quickly. D equals infinity, there are no fluctuations. And there is a synergy or a universality class, which seems to be uncovered here, that places these two in the same universality class. Okay, I'd just like to thank everyone who is involved in this project. Two key students, Jinchao, Gaurav, Nico, a cast of others, and some colleagues, Gabriele, and then Barry was very involved in the orbital construction. And my postdoc, Pei Chumai, who did a lot of the numerics and was sort of an architect of the orbital HK model as well. Okay, there are other people around the world who are starting to pick up on this, and it's doing DMRG in one direction, OHK in the other, but I think that's all the time I have.
Thank you very much. So first question would be to Gabriele Bellomia. I don't know if you're here, if you want to ask your question yourself. The question is in the chat, so I'm gonna read it since Gabriele.
Yes, if you want.
Manifesting.
If you hear me, I can. Okay. No, I'm just a little confused. So when you do the 1D Hubbard model, you do the DMRG solution, you're actually doing a variational ansatz for the solution of the Hamiltonian. So looking at the energies gives
I'm
you...
just looking, I just take the beta ansatz solution for the
Yes.
ground state energy, which is in terms of Bessel functions, and I just evaluated it numerically.
No, right. But when you compare it to the MRG, there is a clear hint at how good the MRG solution is, basing just on the energy. Instead, if you
Right.
take another model, because the orbital Hatsugai Kohmoto construction is a modification of the Hamiltonian, right? Not a variational ansatz. You are looking again at the energies and seeing that they approach very good, very fast, let's say, the exact solution from the beta ansatz. But does the energy gives you the whole story? You better need to compare wave functions, density matrices, or Green's functions, something that talks about every observable, not just the energy, right? That's my
That's
doubt.
why we immediately went and compared with the excitation gap.
Mm.
Okay.
Which is again just one, so two observables instead of all of them.
Yeah. I mean, you know,
Okay.
and once again, I mean, DMRG is very good at ground states. It's sort of problematic with excited states, but
Yes.
you know, I did that. I showed how to improve that by using periodic boundary conditions.
So you never
So, I
compared
mean,
the actual wave function.
Right.
to
Okay. The
yeah.
wave functions. Okay. Yeah. That is something we are working on.
Okay.
Yeah. I mean, that's something to go and do.
Okay. Thank you.
Okay, next, Antoine.
Yes, thanks, Philippe, for your talk. I have a question which is both about magnetism and the connection to DMFT. So if you make the DMFT approximation or solve in the infinite dimensional limit any repulsive Hubbard model on a bipartite lattice, you will find that the ground state is antiferromagnetically ordered for either arbitrarily small u if there is nesting or beyond a critical value of u if there isn't. But it seems that you don't have antiferromagnetism in the ground state at finite n in the OHK model, right? So how can you document the fact that they're in the same universality class if the nature of the coalitions in the ground state are different?
Okay, you know the answer to that question.
Do I?
One is antiferromagnetism is not the central player in Mott physics.
Oh, no, with that, I, of course, completely agree.
Okay. So it cannot be an indicator of a fixed point. Okay. Now, that said, what we are finding is that there are antiferromagnetic correlations, but because of Merman-Wagner, we are not getting that, you know, we have full-blown antiferromagnetism. We're seeing the susceptibility is increasing as you decrease the temperature and as you increase U, but it's never diverging. So I would say the fact that there might be differences, I would put antiferromagnetism as the detail. It is not the thing that controls the fixed point. As we well know, that just goes piggyback on top of the strong correlations.
Okay. Thank you.
Are there any other questions?
Can I ask a question?
Please.
Yes.
Hi, thank you for the talk. I want to ask, you showed that in dimension equal to 2, for every finite interaction, you were able to find a gap opening.
Right.
I was wondering, is this true for any dimension, or this is really, because, I mean, at least in cluster DMFT, this is really a striking, let's say, characteristic of the dimension equal to 2. In this model, is this true also? I mean,
Okay,
only
I don't see why 2 would be special. But it's just right. Yeah, when you include this orbital mixing, it seems as if you get rid of this this critical value of U. And look, that's what all the simulations are getting as well. So I would say that this is not a new statement. We haven't done 3 dimensions, okay? We could easily do it. Okay, it's just that there were bigger fish to fry right now in terms of showing that this really does give results which are on par with what people know.
okay. Not only because I think that in dimension equal to 3, instead you expect that there is a finite U to get the Mott insulator. At least
I
at
haven't
the
done any
cluster
simulations on
level.
that. I mean, is that what the cluster people get? I mean, is that, Antoine, is that the best? Is that the result?
Well, again, I mean, to discuss that question, we will have to decide whether we consider magnetic solutions or not. The answer to the question depends on that.
Yeah, but magnetism is not the origin of the gap. His question is the critical value for the gap.
Well,
Yeah, I mean a paramagnetic solution. I was thinking about
Yeah,
that one.
he's talking entirely about paramagnetism. If you want to peg the gap on antiferromagnetism, then we don't have to go and do all of this. I mean, there's just the standard that has nothing to do with Mottness.
fully agree.
Okay, so
excuse me, can I add a comment to this?
yeah,
Sure.
Yeah, so I think adding more dimension may change the critical value. And also the fact that in 2D, we open a gap at infinitesimal U is due to the Fermi surface nesting. So if we, for example, if we have a T prime, then we will have a finite critical U.
yes, that's
Or
right.
if we work on, instead of square lattice, but a honeycomb lattice, that also make the critical U finite.
Right, yes. I did forget to say that. Yes. So that's Pei Chumai, who is one of the co-authors on all of this work. Yeah, so there is a critical value of U in 2 dimensions if you have T prime.
It should be.
Okay.
Can I ask another quick question, Olivier?
Sure.
Yes, but that's going to be the last.
Yeah. Okay. So I would like to know the opinion of the OHK model about finite temperature Mott transition in highly frustrated lattices. So as you know, one of the contentions or predictions of DMFT is that you can have a first order metal insulator transition at finite temperature, which ends into a second order critical point that has Ising criticality. So what happens in such a situation in the OHK model? Does it also lead to that physics?
No, does it lead to a first order transition?
Well, there is a first order line and a second order critical endpoint, right?
Right. We have not explored that.
Or maybe we can discuss that offline.
Yeah. That would be, as I said, we just wanted to put this out there so it works, and then go and start worrying about further details. But that's something worth looking at.